Hello, and welcome to Space for Sleep. Tonight we are going to travel outward, past the familiar inner planets, past the asteroid belt, past Jupiter and Saturn, past Uranus, and into one of the least visited regions of the planetary solar system. We are going to Neptune. Neptune is not the largest planet. It is not the brightest. It is not the planet most people first imagine when they think of the drama of the solar system. Saturn has its rings. Jupiter has its storms and enormous moons. Mars has its red deserts and its long association with the search for life. Neptune waits farther out, blue and cold, almost hidden at the edge of ordinary planetary maps. And yet Neptune is one of the most scientifically important worlds we know. It is an ice giant, a type of planet that may be closer to the most common planetary category in the galaxy than the rocky worlds we understand more easily. It has the fastest winds measured on any planet in the solar system. It releases more internal heat than it receives from the distant sun. It has a magnetic field tilted and shifted so dramatically that it seems to come from somewhere off-center inside the planet. It has dark storms that appear and vanish. It has rings that are faint, incomplete, and held in place by delicate gravitational resonances. And it has Triton, a captured moon from the Kuiper Belt, orbiting backward, geologically active, and slowly spiraling toward a future destruction that may one day give Neptune a ring system worthy of Saturn. This is a world we have visited only once. Voyager 2 flew past Neptune in August of 1989, gathered what it could in a brief encounter, and then continued outward into interstellar space. No orbiter has ever settled around Neptune. No probe has ever entered its atmosphere. No lander has ever touched Triton. Much of what we say about Neptune is therefore built from a combination of one extraordinary spacecraft flyby, decades of telescope observations, and careful physical modeling. That makes Neptune a good world for a long, quiet journey. It is not fully known. It still has gaps, uncertainties, unfinished questions. But those gaps are not weaknesses in the story. They are part of what makes Neptune worth studying. Science is not only a list of confirmed facts, it is also the patient mapping of what we do not yet understand. So tonight we will move slowly. We will begin with the strange story of Neptune's discovery, because this was the first major planet found by mathematics before it was recognized by sight. We will then travel outward to understand its distance, its orbit, its seasons, and the weakness of sunlight so far from the sun. We will descend into its blue atmosphere and the extreme winds that move through it. We will move deeper into its strange interior, where water, ammonia, and methane are compressed into states of matter that do not exist naturally on Earth's surface. We will look at its magnetic field, its faint rings, its small moons, and finally Triton, one of the most important and mysterious moons in the outer solar system. There is nothing you need to memorize. Let the science arrive clearly, and let the pace remain calm. This is a story about a planet almost 5 billion kilometers from the sun, a world that has been turning in the dark for 4.5 billion years, mostly unseen, mostly unvisited, but not simple. Let's begin. To understand why Neptune's discovery is one of the great intellectual achievements in the history of astronomy, you need to understand what a strange and counterintuitive thing it was to find a planet using mathematics rather than observation. Every planet discovered before Neptune was found by simply looking at the sky and noticing something that moved against the background of stars. Mercury, Venus, Mars, Jupiter, and Saturn were known to ancient observers thousands of years before the telescope was invented. Their steady, wandering motion across the constellations was obvious enough to attract attention and mythology in cultures around the world. Uranus, discovered in 1781 by William Herschel, was also found by direct observation. Herschel noticed a faint disc-like object in his telescope, initially thought it was a comet, and eventually realized it was a new planet, the first discovered in the era of the telescope. Neptune was different. Neptune was found by prediction. After Uranus was discovered and its orbit calculated, astronomers began noticing something troubling. Uranus wasn't quite moving the way it should. Its observed position in the sky didn't match its predicted position. The discrepancies were small, tiny fractions of a degree, but they were real, they were consistent, and they grew over time in ways that couldn't be dismissed as measurement error. Uranus was being pulled off course by something with enough gravitational mass to perturb the orbit of a planet sitting somewhere in the outer solar system, not yet discovered. Two mathematicians, working independently, set out to find that something using only mathematics. Urbain Le Verrier in France and John Couch-Adams in England both tackled the same problem. Given the observed perturbations in Uranus's orbit, what mass would be required to cause them, and where in the sky would that mass have to be? Both performed painstaking calculations, applying Newton's laws of gravity to work backward from the orbital irregularities to a predicted position for the unknown planet. Adams completed his calculations first, in 1845, and communicated his results to the British Astronomer Royal, George Biddell Airy, who received the communication with skepticism and delayed acting on it. Le Verrier completed his own independent calculations in 1846 and communicated them to the German astronomer Johann Gottfried Galle at the Berlin Observatory, who immediately pointed his telescope to the predicted position on the night of September 23, 1846, and found Neptune within 1 degree of where Le Verrier had predicted, essentially exactly where the mathematics said it had to be. It was one of the most dramatic confirmations of Newtonian physics ever performed. Two scientists in two countries had looked at the same orbital wobble in a distant planet and, using the same mathematical laws that Newton had written down nearly 2 centuries earlier, had pointed to nearly the same spot in the sky, and a planet was waiting there, exactly as predicted. It was an extraordinary intellectual triumph, and the announcement of Neptune's discovery was one of the great scientific events of the 19th century. The question of credit between Adams and Le Verrier generated diplomatic friction between Britain and France for years afterward, each nation claiming priority for its citizen, a dispute that historians of science still discuss today. The modern consensus generally gives both men significant credit while acknowledging that Le Verrier's calculation led directly to the telescopic discovery, since it was acted upon promptly, while Adams's prediction was delayed by institutional caution on the British side. What matters scientifically is not the priority dispute but the achievement. A planet was found not by looking for it, but by calculating where it had to be. It was the first time in history that a major astronomical object was discovered purely through theoretical prediction, and it demonstrated something profound about the reach of mathematical physics. The universe, at least in its planetary mechanics, was organized by laws that human beings had worked out and could use to find things they had never seen. The solar system was knowable in a new and deeper way than it had been before. When Galle pointed his telescope to the predicted location and found Neptune there, he was, without quite intending to, proving that gravity was not just a description of what we had already observed but a genuine tool for exploring what we hadn't yet seen. The implications of that proof have echoed through physics ever since. The discovery of Neptune also shows how fragile scientific discovery can be. The planet was present in the sky the whole time. It had been passing through star fields for centuries, faint but not impossibly faint, visible to telescopes long before anyone understood what it was. The obstacle was not the absence of light. The obstacle was interpretation. That distinction matters. Astronomy is full of objects that were first seen before they were understood. Uranus was recorded before it was recognized as a planet. Neptune was drawn by Galileo before it was named. Quasars appeared on photographic plates before anyone understood they were the blazing cores of galaxies. Pulsars first appeared as radio signals before their connection to neutron stars was accepted. In each case, the data arrived before the concept was ready to receive it. Neptune's discovery therefore belongs to a broader history of science, the history of learning how to see. A telescope gives the eye more power, but mathematics gives the mind more reach. Without the theory of gravity, Neptune would have been merely another faint point. With the theory of gravity, that faint point became the answer to a problem written in the motion of Uranus. This is why Neptune still has symbolic importance in astronomy. It is not only the eighth planet. It is proof that invisible things can be detected by their effects. The same logic now runs through much of modern astrophysics. We infer exoplanets from the tiny dimming of starlight when they pass in front of their stars, or from the small wobble they impose on their host stars through gravity. We infer dark matter from the motions of galaxies and the bending of light. We infer black holes from the stars that orbit them and the radiation produced by matter falling toward them. Neptune was an early, elegant version of this idea, the unseen made visible through consequence. That makes the story of its discovery more than a historical anecdote. It is a lesson in how science often works at its best, not by guessing wildly and not by waiting passively, but by noticing a small mismatch between prediction and observation, refusing to ignore it, and following that mismatch patiently until it points to something real. The priority dispute between Adams and Leverrier is worth dwelling on a little longer because it tells us something interesting about how science actually works, about the difference between doing a calculation and acting on it, between intellectual achievement and operational discovery. Adams completed his predictions in September 1845, roughly a year before the telescopic discovery, and submitted them to the British Astronomer Royal, George Biddell Airy. Airy, a cautious administrator who had seen many confident astronomical predictions fail to pan out, was skeptical. He replied to Adams with a question about a technical detail of Neptune's predicted orbit, an answer to which might have resolved some of his doubts. And Adams, who was young, shy, and perhaps not aggressive enough in pushing his case, replied only after a significant delay. Airy, still not fully convinced, eventually agreed to organize a search, but did so slowly, with the search beginning only in late July 1846, months after he first learned of Adams's prediction. Leverrier, meanwhile, submitted his own independent calculation to the Berlin Observatory in September 1846, along with a direct request to search the predicted position. Gao received the letter on the evening of September 23, 1846, and that very same night searched for and found Neptune. The British search, organized months before but proceeding slowly through methodical comparison of observations with star charts, had also observed Neptune several times in the preceding weeks. But the observers, not knowing they'd found a planet, hadn't looked for the slight disk shape that would distinguish a planet from a star among the dense field of objects in that region of sky. They missed it. Gao, given an explicit, urgent prediction and looking specifically for a planetary disk, found it immediately. The sequence of events created a genuine scientific controversy. England claimed Adams deserved credit for the mathematical prediction. France claimed Leverrier deserved credit because his prediction led directly to the discovery. The dispute was complicated by the fact that both men had done essentially the same calculation and reached essentially the same answer. A remarkable demonstration of how a well-posed mathematical problem, approached with sufficient skill, yields a unique, reproducible answer regardless of who solves it. The resolution, in retrospect, has been that both men are given credit for the prediction, with the discovery itself attributed to Gao and his colleague D'Arrest, who assisted in the search. Adams and Leverrier actually met personally in 1847 and reportedly got along well. unbothered by the political fury that their respective national champions were waging on their behalf. The planet itself is named Neptune, the Roman god of the sea, a name proposed by Voyager, though Gal initially wanted to name it Janus. Neptune stuck, continuing the tradition of naming planets after Roman gods. Even Neptune's naming quietly reflects the way humans try to fit new discoveries into older patterns. Once the planet was found, it needed a name. The tradition of naming planets after Roman gods was already well established, and the blue color of the planet made Neptune, the god of the sea, feel especially appropriate. The name also fit the outer solar system's pattern of mythological families. Neptune's largest moon became Triton, named after the sea god's son. Later moons were named after lesser sea deities and nymphs. The rings were named after astronomers connected with Neptune's discovery and study. These names are human additions. Neptune does not know it is Neptune. Triton does not know it is Triton. But naming is one of the ways we create a relationship with places too distant to touch. A faint blue planet becomes not merely a coordinate in the sky, but a world with a story, a history, a family of moons, and a place in the mental map of the solar system. There is a useful caution here. Names can make worlds feel familiar before we truly understand them. We say Neptune, and the name becomes simple, almost ordinary. But behind that simple name is a planet with winds faster than sound in Earth's atmosphere, a deep interior of compressed fluids, a tilted magnetic field, faint rings, a captured moon, and a discovery story that changed the meaning of prediction in astronomy. The name is easy. The world is not. The discovery also led to a quiet but important secondary investigation. Researchers went back through historical records of astronomical observations and found that Neptune had in fact been observed before its official discovery, most notably by Galileo, who had seen it twice in late 1612 and early 1613, drawn it in his notebooks as a star, and noticed that it appeared to have moved slightly between observations, though he did not pursue the matter further. Had Galileo been looking for a new planet, he might have found Neptune more than 2 centuries before Voyager and Adams. As it was, his observations became, retroactively, the earliest known recorded sightings of the planet. Observations made when the astronomer had no idea he was seeing anything unusual. This detail, that Neptune was seen and not recognized, observed and not understood, present in the data but invisible to interpretation, is a quiet reminder that discovery is not just about gathering observations. It is about having the right framework to understand what you're seeing. Galileo had the observations. What he lacked was a reason to think a planet might be there, and so he saw only a faint, slightly mobile star in a crowded field and moved on. Let's also take a moment to fully appreciate the scale of Neptune's remoteness, because numbers like 4.5 billion kilometers can become meaningless through repetition. Light travels at approximately 300,000 kilometers per second. In 1 second, light crosses a distance roughly equal to 7.5 times Earth's circumference. In 8 minutes and 20 seconds, it crosses the distance from the Sun to Earth. Neptune is so far from Earth that light takes more than 4 hours to make the journey one way. More than 4 hours of travel at the fastest possible speed in the universe, just to cross the gap between our planet and Neptune when they're on the same side of the Sun. When they're on opposite sides, the distance and the travel time nearly double. A radio signal from a spacecraft at Neptune, radio waves also traveling at the speed of light, takes more than 4 hours to reach Earth. Which means that when Voyager 2 sent back its images of Neptune in 1989, the scientists watching those images appear on monitors at the Jet Propulsion Laboratory were seeing events that had already happened more than 4 hours earlier. The spacecraft's commands, sent from Earth, took 4 hours to arrive at the spacecraft. If something went wrong, The spacecraft would be on its own for 8 hours minimum before a correction command could even begin to have any effect. Managing a spacecraft at that distance requires a different kind of planning than managing one in Earth orbit or even at Mars. You must anticipate everything, because by the time you know something has gone wrong, the opportunity to fix it may already have passed. The Pioneer 10 spacecraft, which was aimed at Jupiter and passed through the outer solar system in the early 1970s, crossed Neptune's orbit distance in 1983. Pioneer 11 crossed it around the same time. Voyager 1, which took a different trajectory after Saturn, crossed Neptune's orbital distance in 1990, shortly after Voyager 2's flyby. New Horizons, the fastest spacecraft ever launched, which flew past Pluto in 2015, crossed Neptune's orbit in 2007 on its way outward. These crossings are milestones noted with a certain quiet ceremony in mission documentation, the moment when a spacecraft leaves the realm of the major planets and enters the true outer solar system. And yet, even Neptune's orbit is not the edge of the solar system. The Kuiper belt extends to about 50 astronomical units. The scattered disk reaches further. The hypothetical Oort cloud, the vast sphere of cometary nuclei thought to surround the solar system at distances of 10,000 to 100,000 astronomical units, is so immensely far beyond Neptune that Neptune's orbit, at 30 astronomical units, represents only a tiny fraction of the solar system's total extent. Neptune is at the edge of the planetary solar system, but not at the edge of the solar system itself. What lies between Neptune's orbit and the Oort cloud is the Kuiper belt and the scattered disk, a population of hundreds of thousands of icy objects, from small pebbles to dwarf planets, orbiting in a vast, cold, dark region of space that we have only begun to explore. Pluto, demoted from planetary status in 2006, is the most famous Kuiper belt object, but there are others of comparable size: Eris, Makemake, Haumea, Sedna, and dozens more, and an unknown but potentially enormous population of smaller objects that current surveys are still cataloging. There is another way to feel Neptune's distance. Imagine the solar system as a walk. If Earth orbited the Sun at a distance of 1 meter in a scale model, Neptune would orbit at about 30 meters. The Sun itself would be a small glowing ball at the center, and Earth would be close enough that you could reach it after only a few steps. Mars would be a little farther out. Jupiter would already feel distant. More than 5 meters from the Sun. Saturn would sit nearly 10 meters away. Uranus would be about 19 meters out, and Neptune would be at 30 meters, in a colder, emptier part of the room, beyond where the bright central light feels warm. Now imagine extending that same model to the Kuiper belt. Pluto, depending on where it is in its elliptical orbit, would drift around the outer region, sometimes closer to the Sun than Neptune, but usually farther out. The edge of the classical Kuiper belt would reach roughly 50 meters. But the Oort cloud, if represented on the same scale, would not fit in the room, the building, or even the neighborhood. It would stretch for many kilometers. This is why saying Neptune is at the edge of the solar system is both useful and misleading. It is the outermost major planet, the last of the 8, the final giant. But beyond it lies an enormous dark architecture of icy bodies, scattered worlds, comet reservoirs, and objects so distant that sunlight barely holds them. From Neptune, the Sun would still be bright, but it would no longer feel like the central presence it is from Earth. It would be a brilliant point, not a broad disk. Noon on Neptune would be dim compared with a clear day on Earth, closer to a deep twilight. The planet is still governed by the Sun's gravity, still warmed slightly by sunlight, still part of the same solar system, but it lives in a different solar experience. It is a world of weak light and long time. Neptune, orbiting at the inner edge of this vast outer region, is the gravitational shepherd of the Kuiper belt, its gravity organizing and resonating with the objects beyond in patterns that have shaped their distribution over the entirety of solar system history. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers, nearly 30 times farther from the Sun than Earth. At that distance, light from the Sun takes approximately 4 hours and 10 minutes to reach Neptune. Think about that for a moment. The sunlight that illuminates Neptune's blue cloud tops left the Sun more than 4 hours ago, traveling at 300,000 kilometers per second the entire time, before finally arriving at that cold, remote world. By the time it gets there, it has faded to about 1/900th of its intensity at Earth's distance, enough to mark day from night, but nothing like the warmth and brightness we associate with sunlight here. If you could stand on Neptune's cloud tops, which you couldn't, for reasons we'll come to, but as a thought experiment, the Sun would appear not as the large, warm disk we know, but as an intensely bright point of light, about the size of a large, very bright star as seen from Earth. It would be the brightest object in the sky by a vast margin, still far too bright to look at directly, but small and cold and distant in a way the Sun from Earth never feels. Neptune's orbit is nearly circular, more circular than Mars or Mercury, though slightly less so than Venus or Earth. It takes Neptune approximately 164.8 Earth years to complete one orbit around the Sun. This means that since Neptune's discovery in September 1846, the planet has completed just slightly more than one full orbit. It returned to the approximate position in the sky where Gal first spotted it in 2011, completing its first full observed orbit since discovery. In the entire history of human civilization, since ancient Mesopotamia, since the construction of the pyramids, since the Roman Empire, since the Renaissance, Neptune has completed only about 25 or so full orbits around the Sun. It moves so slowly against the background of stars that any given generation of astronomers sees it in essentially the same part of the sky as the previous generation. Neptune's great distance from the Sun means it receives far less solar energy than the closer planets. And yet, despite that enormous distance and the meager warmth arriving from the Sun, Neptune radiates more heat into space than it receives, about 2.5 times more. Like Jupiter, Neptune has an internal heat source, a relic of its formation, still slowly releasing heat into space billions of years after the planet first formed. This internal heat, as we'll discuss when we come to Neptune's interior, is a major driver of the atmospheric dynamics that produce the most extreme winds in the solar system. Neptune's axial tilt is about 28 degrees, close to Earth's 23.5 and Mars's 25, though slightly more inclined than either. This tilt gives Neptune seasons, but because a Neptunian year spans 165 Earth years, each season lasts roughly 40 Earth years. The northern summer, the southern winter, a long and barely perceptible transition between them, all unfolding across timescales that dwarf the entirety of recorded human history. A person born at the beginning of a Neptunian summer would die of old age long before that summer ended. Neptune's formation is tied to one of the great puzzles in planetary science: how the outer planets ended up where they are. In the simplest picture, planets form where we find them. Dust and ice collect in the disk around the young sun. Small grains become pebbles. Pebbles become planetesimals. Planetesimals become planetary embryos. And eventually the embryos grow into planets. But the outer solar system does not appear to have formed in such a simple, static way. Neptune is too far out, and the density of the original disk at its current orbit may have been too low for the planet to grow efficiently in the time available before the solar nebula dispersed. This is one reason many models suggest that Neptune formed closer to the Sun than it orbits today, in a denser region of the young planetary disk, and then migrated outward. Its movement was not smooth in the way a planet on a rail would move. It was the result of countless gravitational exchanges with smaller icy bodies. Every time Neptune scattered a planetesimal inward or outward, a tiny amount of angular momentum was exchanged. Multiplied over millions of bodies, those small exchanges could shift the orbit of an entire planet. This outward migration is central to modern models of the early solar system. It helps explain why Pluto is locked in a stable resonance with Neptune. It helps explain the structure of the Kuiper belt, with its resonant populations, cold classical objects, scattered objects, and highly inclined or eccentric orbits. It may also help explain the timing of bombardment events in the inner solar system, when objects from the outer regions were destabilized and sent inward. In this sense, Neptune is not simply sitting at the edge of the planetary system. It helped build that edge. It migrated through a disk of icy bodies, capturing some into resonances, scattering others into elongated orbits, and shaping the region that would later become known as the Kuiper belt. The present solar system is not a frozen arrangement from birth. It is the result of movement, migration, loss, and long gravitational sorting. The same principle applies to planetary systems around other stars. Many exoplanets are found in places where they likely did not form. Hot Jupiters, for example, orbit extremely close to their stars, but are thought to have formed farther out and migrated inward. Resonant chains of planets around other stars suggest histories of movement through disks. Neptune, in our own solar system, gives us a local example of how a planet's current orbit can be the end of a journey rather than the place where its story began. Neptune is classified as an ice giant, a category it shares with Uranus and which distinguishes both from the gas giants Jupiter and Saturn. The distinction matters because Neptune's interior is fundamentally different from what lies inside the larger gas giants, and those differences drive much of what makes Neptune so unusual. The planet's diameter is about 49,500 kilometers, roughly 4 times Earth's diameter, and slightly larger than Uranus. Its mass is about 17 times Earth's mass, making it the third most massive planet in the solar system after Jupiter and Saturn, despite being slightly smaller in diameter than Uranus. Neptune is denser than Uranus, more mass-packed into a slightly smaller volume, and this density difference reflects meaningful differences in their interiors and histories. Surface gravity on Neptune, at the cloud tops, is approximately 1.14 times Earth's surface gravity, almost exactly the same as you'd feel on Earth, which is a somewhat surprising coincidence given how different the planet is in almost every other way. A person standing on Neptune's cloud tops would weigh about 14% more than on Earth, barely perceptible in everyday experience, though the rest of the environment would immediately make itself known in ways rather more dramatic than a slight increase in weight. Neptune rotates once on its axis in approximately 16 hours and 6 minutes, faster than Earth's 24-hour day, but slower than Jupiter's 10 hours. This rotation is fast enough to flatten the planet noticeably at its poles and bulge it at its equator, and fast enough to organize its atmospheric circulation into the powerful, banded jet streams that drive Neptune's extraordinary winds. The rotation period was actually difficult to determine precisely from Earth-based observations, and Voyager 2's magnetometer measurements, which tracked the rotation of Neptune's magnetic field as a proxy for the planet's interior rotation, gave the most precise measurement we have. When Voyager 2 sent back its first color images of Neptune in 1989, many people were surprised by what they saw. Neptune is blue. Not the pale blue of Earth's oceans and atmosphere, not the vague blue-gray of Uranus, but a vivid, deep, almost electric blue that looks almost artificial in photographs. Too saturated, too intense, too uniformly gorgeous to seem like a natural planetary atmosphere. And yet it is entirely natural. Neptune's striking blue color comes from the presence of methane in its atmosphere, which absorbs red wavelengths of light and scatters blue wavelengths preferentially back toward the observer. The same process occurs on Uranus, which also contains methane. But Neptune appears distinctly bluer and more saturated than Uranus, even though the two planets have broadly similar atmospheric compositions, and the reason for this deeper, richer blue is not fully understood. Some additional absorbing agent, something not yet precisely identified in Neptune's atmosphere, may be contributing to the color, making it appear more intensely blue than methane alone would explain. Neptune's atmosphere is composed primarily of hydrogen, about 80%, with helium making up most of the remainder, and a small but significant fraction of methane, around 1 to 2%, plus trace amounts of ammonia, ethane, acetylene, and other hydrocarbons. This composition is broadly similar to the other giant planets, but the presence of methane is proportionally larger than in Jupiter or Saturn, and it's this methane that dominates the visual appearance. The atmosphere is divided into layers of increasing pressure and temperature with depth. The cloud tops that define the visible surface of Neptune are made of methane ice, and below them are layers of ammonia ice and water ice clouds at higher pressures and temperatures. The atmosphere is not static. It churns and circulates, driven by both the rotation of the planet and the internal heat rising from below, producing the dynamic, complex, rapidly changing weather systems that Voyager 2 found so dramatically different from the calmer appearance of Uranus. The upper stratosphere of Neptune, where ultraviolet light from the sun drives photochemistry, is a chemically active region where methane molecules are broken apart by solar radiation, their fragments recombining into more complex hydrocarbons, ethane, acetylene, diacetylene, and others, that form a thin photochemical haze above the main cloud layers. This haze absorbs ultraviolet light and contributes to warming the stratosphere somewhat, though as noted earlier, the stratosphere is still warmer than solar heating alone would explain, suggesting additional heat sources are at work. At the cloud top level, where most of the visible weather occurs, the wind patterns are organized by Neptune's rapid rotation into latitudinal bands. The most intense winds occur near the equator, blowing in the retrograde direction at speeds up to about 2,100 kilometers per hour. Moving toward the poles, the wind speeds diminish and the direction changes, with mid-latitude and polar winds blowing in the prograde direction. This pattern of retrograde equatorial winds surrounded by prograde mid-latitude and polar winds is similar to Uranus and fundamentally different from the equatorial jets of Jupiter and Saturn, and its origin remains an open question in planetary atmospheric science. One of the fascinating details of Neptune's visible atmosphere is how rapidly it changes compared to the more slowly evolving storms of gas giants. The Great Dark Spot that Voyager 2 observed in 1989 was gone by the time Hubble first observed Neptune in 1994. New dark spots have appeared and disappeared in the years since. Bright cloud features that Voyager's mission scientists nicknamed informally come and go on timescales of weeks to months, forming as gas rises and methane condenses in the cold upper atmosphere, then dissipating as conditions change. Neptune's atmosphere is genuinely restless, more rapidly variable, in terms of visible weather features, than any of the other giant planets. There are also hints that Neptune's overall appearance changes over longer timescales. Observations spanning decades suggest that Neptune's brightness and the prevalence of cloud cover vary in ways that may be linked to its seasons. The 40-year seasons driven by its axial tilt and 165-year orbital period. As Neptune's southern hemisphere has moved from summer into autumn and the northern hemisphere from winter into spring over recent decades, the distribution of cloud features and the overall reflectivity of the planet may be responding to the changing solar illumination of different regions. Studying these long-term changes requires consistent, high-quality observations spanning decades, and astronomers using Hubble and large ground-based telescopes have been building up that record year by year. Neptune's atmospheric chemistry extends in detail that Voyager's instruments could only begin to characterize. Future spectroscopic observations and eventually a future mission with atmospheric probes could dramatically improve our understanding of the chemical composition at different depths, the vertical temperature structure, and the processes that drive Neptune's energetic weather. Each layer of the atmosphere tells a different story. The hazy stratosphere, the methane cloud tops, the deeper ammonia and water clouds at increasing pressure, and the eventual transition to the supercritical fluid of the interior. And each layer's story is intertwined with the others in ways that make Neptune's atmosphere a complex, multi-layered system that rewards detailed study. The blue color of Neptune is often treated as a simple fact, but even that color contains a scientific puzzle. Methane explains part of it. Methane absorbs red light and allows more blue light to be scattered back to space, which is why both Uranus and Neptune appear blue-green. But Uranus and Neptune are not the same color. Uranus tends to look paler, more cyan, more softly blue-green. Neptune appears deeper, richer, more saturated. For a long time, this difference was partly exaggerated by image processing, because early Voyager images were often enhanced to bring out cloud features. But even when the colors are treated carefully, Neptune and Uranus do not look identical. Something in their hazes, cloud layers, or atmospheric chemistry differs. Recent work suggests that the thickness and distribution of aerosol haze layers may explain much of the visual difference. A thicker haze on Uranus may lighten and desaturate its appearance, while Neptune's clearer upper haze allows the deeper methane blue color to show more strongly. This is a good example of a larger truth about planetary atmospheres. Color is not only composition. It is also particle size, altitude, haze thickness, cloud depth, and the way light scatters through layers before escaping back into space. Neptune's clouds are also built differently from clouds on Earth. On Earth, most familiar weather is driven by water vapor changing phase, evaporating, condensing, freezing, and releasing latent heat. On Neptune, water is mostly far deeper in the atmosphere, at pressures and temperatures far beyond the visible cloud tops. The visible high clouds are more likely methane ice, forming where methane vapor rises into colder regions and condenses. Beneath those clouds, at greater depths, there may be layers of hydrogen sulfide, ammonia, and water clouds, each forming where the pressure-temperature conditions allow that material to condense. This layered atmosphere is difficult to study from far away. A telescope sees the light that escapes from upper layers, not the deep convective machinery beneath. By observing Neptune at different wavelengths, astronomers can probe different altitudes. Visible light shows the broad blue disk and some high clouds. Near-infrared wavelengths can reveal methane, cloud activity, and deeper features. Ultraviolet observations can study hazes and photochemistry. Thermal infrared observations can map temperatures in the stratosphere. Each wavelength is like a different window into the same atmosphere, but none of them alone gives the whole structure. This is one reason Neptune needs an orbiter or an atmospheric probe. A probe descending through the atmosphere could directly measure temperature, pressure, wind, methane abundance, noble gases, isotopic ratios, and cloud layers. These measurements would not only tell us about Neptune's weather, they would tell us about how and where the planet formed, because the ratios of elements and isotopes in the atmosphere preserve clues about the materials Neptune collected during its birth. One of the most important and puzzling features of Neptune's atmosphere involves the temperatures at different altitudes. The stratosphere of Neptune, the upper atmospheric layer, is significantly warmer than it should be if the only heat source were solar radiation at Neptune's distance. Neptune is so far from the Sun that solar ultraviolet radiation alone shouldn't be enough to heat the stratosphere to the temperatures observed. Something else must be contributing. Various explanations have been proposed, including the absorption of solar energy by haze particles in the upper atmosphere, heating by gravity waves propagating upward from the lower atmosphere, and other mechanisms. The precise explanation is still debated, and it represents one of the puzzles about Neptune's energy balance that future missions and improved observations are needed to resolve. The most immediately striking feature of Neptune's atmosphere, when Voyager 2 arrived in 1989, was a storm the size of Earth sitting in the southern hemisphere. It was called the Great Dark Spot, a dark, oval-shaped system of anticyclonic circulation, rotating counterclockwise, with bright methane ice clouds forming along its edges as atmospheric gas was forced upward around the storm's margins and cooled to the condensation point. The Great Dark Spot was reminiscent, at first glance, of Jupiter's Great Red Spot, a large, persistent storm dominating the planet's weather. But it was different in character. Where Jupiter's Great Red Spot has been observed continuously for centuries, Neptune's Great Dark Spot had disappeared entirely by the time the Hubble Space Telescope observed Neptune in 1994, only 5 years after Voyager 2's flyby. In its place, a new dark spot had formed in the northern hemisphere. Neptune's atmospheric storms, it turned out, are not permanent features but relatively transient ones, appearing and disappearing over years or decades rather than centuries. At the time of Voyager 2's flyby, the Great Dark Spot was the dominant feature of Neptune's visible weather. Wind speeds around its margins reached approximately 2,100 kilometers per hour, by far the fastest sustained wind speeds ever measured on any planet in the solar system. To put that in human terms, the fastest wind gust ever recorded in any storm on Earth's surface was just over 400 kilometers per hour, measured during Tropical Cyclone Olivia in 1996. Neptune's Great Dark Spot routinely exceeded 5 times that speed. A wind at 2,000 kilometers per hour is not weather in any sense that human experience has prepared you for. It is a force that would reduce any structure humanity has built to debris within moments. What makes Neptune's winds even more remarkable is their direction. Near the equator, Neptune's atmospheric winds blow in the direction opposite to the planet's rotation. They blow westward, while the planet itself rotates eastward. This retrograde equatorial wind pattern is shared with Uranus, and it is not well understood. On Earth and on Jupiter and Saturn, equatorial winds blow in the same direction as the planet's rotation, driven by the thermal dynamics of the tropics. On the ice giants, the equatorial winds go the other way. Understanding why requires understanding the deep structure and heat transport mechanisms in the ice giant interior, which are still poorly constrained. The internal heat that Neptune radiates, more than twice what it receives from the Sun, is the primary driver of its atmospheric dynamics. Unlike Uranus, which radiates only as much heat as it receives, making Uranus the thermally coldest planet in the solar system at its cloud tops, Neptune has a significant internal heat source powering its weather. The origin of this heat is still debated. It's almost certainly residual heat from Neptune's formation, slowly leaking out. The same general category of explanation that applies to Jupiter's excess heat. But the details of why Neptune retains so much more internal heat than similarly sized Uranus, despite their broadly similar compositions and formation conditions, remain an open and genuinely puzzling question. Some models suggest differences in their interior structures, in how efficiently heat is transported from the deep interior to the surface, account for the difference, but a definitive answer has not been established. Beyond the Great Dark Spot and the wind patterns, Voyager 2 observed numerous other atmospheric features during its brief flyby. Scooter, a bright, fast-moving cloud feature that moved around Neptune faster than the Great Dark Spot, earned its nickname from mission scientists who watched it race across the cloud tops in real time. Smaller dark spots, bright methane clouds at various latitudes, complex banding and layering in the atmosphere, all suggesting a weather system of genuine dynamism and complexity, a planet whose atmosphere was far more active and changeable than Uranus's apparently featureless, bland exterior. Since Voyager 2's departure, Hubble has continued to observe Neptune's atmospheric evolution, watching the Great Dark Spot disappear, watching new spots form and dissipate, tracking the appearance and movement of bright cloud features that come and go on timescales of weeks to months. The planet's appearance has changed noticeably since 1989. Storms have come and gone. The distribution of bright cloud features has shifted, and there are hints that the overall brightness and cloud structure of Neptune may be varying on longer timescales, perhaps related to seasonal changes as Neptune slowly progresses through its 40-year-per-season cycle. Pinning down these longer-term variations from Earth-based observations is difficult. A single Hubble snapshot is like trying to understand Earth's climate from a single aerial photograph, but the data accumulating over decades of Hubble monitoring is beginning to reveal patterns. Neptune's dark spots are especially interesting because they are both familiar and alien. They are familiar because they are vortices, rotating atmospheric systems, shaped by pressure gradients and planetary rotation, in the same broad family of phenomena as hurricanes, anticyclones, and polar vortices on Earth. They are alien because they occur in an atmosphere of hydrogen, helium, and methane, under sunlight hundreds of times weaker than Earth's, on a planet with no solid surface, no ocean underneath the storm, and internal heat rising from deep within an ice giant interior. The Great Dark Spot Voyager saw in 1989 was not a hole in the atmosphere, nor was it a solid feature. It was a region where aerosols and clouds were arranged differently, allowing a deeper, darker atmospheric layer to show through. Modern observations of Neptune's dark vortices suggest that at least some of them may be associated with changes in a deeper aerosol or cloud layer rather than with high-altitude clouds alone. In simple terms, the spot appears dark because light is being absorbed or scattered differently within the storm system, not because the planet has a literal dark surface beneath. Bright companion clouds often form near the edges of these dark spots. These clouds are thought to be methane ice clouds produced when gas is forced upward around the vortex, expands, cools, and allows methane to condense. This is similar in basic principle to orographic clouds on Earth, which form when air is forced up over mountains. Except on Neptune, there are no mountains. The storm itself creates the upward motion. The vortex becomes its own invisible topography in the atmosphere, making clouds where the flow rises along its margins. The disappearance of dark spots is also scientifically important. Jupiter's Great Red Spot has persisted for centuries, though it is changing in size and shape. Neptune's dark spots vanish on timescales of years. That suggests a different balance of forces, a different atmospheric stability, and possibly different vertical coupling between the cloud layers and deeper weather systems. Neptune's atmosphere may generate intense storms easily, but not maintain them for as long. Because Neptune's seasons are so long, it is difficult to separate short-term weather from long-term climate. A decade of observations on Earth is more than enough to see seasonal cycles repeat many times. A decade on Neptune is only a small fraction of one season. The Hubble Space Telescope's long-running observations of the outer planets have begun to reveal changes in Neptune's cloud activity over time, including periods when mid-latitude clouds nearly vanished and later returned. But we are still watching a tiny slice of a very long seasonal story. To understand what Neptune truly is, you have to go inside it. because Neptune's interior is where its most unusual properties originate. Neptune and Uranus are called ice giants, but the term can be misleading. The ice in ice giant doesn't refer to ordinary frozen water, though water is certainly one of the ingredients. It refers to materials that, in the cold outer solar system, condense or freeze at temperatures far above what we'd call room temperature, but far below what exists in the cores of gas giants. These materials, water, ammonia, and methane, are in a hot, dense, compressed state deep inside Neptune that is neither the solid ice of an iceberg nor the gas of Earth's atmosphere, but a supercritical fluid, or perhaps even a liquid, compressed to conditions so extreme that their molecular behavior bears little resemblance to anything in everyday experience. The fundamental distinction between ice giants like Neptune and Uranus and gas giants like Jupiter and Saturn lies in their bulk compositions. Jupiter and Saturn are made overwhelmingly of hydrogen and helium, the lightest elements, with heavier elements playing a relatively minor role. Neptune and Uranus, by contrast, contain a much larger fraction of heavier, icy materials, water, ammonia, methane, relative to their total mass. Perhaps 10 to 20% of Neptune's mass is hydrogen and helium, with the rest being the heavier ices and the rocky metallic core. This compositional difference reflects where and how they formed in the early solar system. The gas giants formed in a region where the solar nebula was dense enough for them to capture enormous envelopes of hydrogen and helium, while Neptune formed farther out, where hydrogen and helium were less abundant and slower to accumulate, leaving the ice-dominated composition we see today. The interior of Neptune is thought to have three broad regions. The outermost is the hydrogen-helium-methane atmosphere we've already discussed, extending down to increasing pressures where the gas blends gradually into a denser state. Below that, making up the bulk of the planet's volume, is the mantle, sometimes called the water-ammonia ocean or the hot ice layer, though neither description quite captures how strange it actually is. This layer is composed primarily of water, ammonia, and methane under enormous pressure and temperature. Temperatures in the range of 2,000 to 5,000 degrees Celsius, pressures millions of times greater than Earth's atmospheric pressure. Under these conditions, the materials behave as a highly compressed, electrically conducting fluid. Water molecules in this layer may be partially ionized, hydrogen atoms dissociating from their oxygen atoms and flowing freely through the mixture, making the mantle a good electrical conductor. This electrical conductivity is what makes the mantle the likely source of Neptune's magnetic field. A conducting fluid in convective motion generates a magnetic field by dynamo action, the same process that generates Earth's magnetic field in the liquid iron outer core, but operating in a very different material at very different depths. The key difference between Neptune's mantle dynamo and Earth's core dynamo is location. Earth's magnetic dynamo operates deep in the planet, in a relatively thin shell of convecting iron. Neptune's mantle dynamo, if the models are correct, operates throughout a large fraction of the planet's volume, in a material whose convection patterns are complex and likely turbulent. The resulting magnetic field would naturally be more complicated, more irregular, more offset from the rotation axis than a deep core dynamo produces, exactly what we observe. In this sense, Neptune's unusual magnetic field is a direct window into its unusual interior structure. At the very center of Neptune, there is believed to be a rocky or metallic core, possibly similar in composition to Earth's interior, silicates, iron, and heavier elements, with a mass somewhere around 1 to 2 times Earth's total mass. This core is under pressures and temperatures that exceed anything that can be replicated in any laboratory on Earth. The exact state of this core material, whether it is solid, partially molten, or in some exotic high-pressure phase that has no ordinary condition analog, is unknown. And then there is the diamond rain hypothesis. At pressures of several million atmospheres and temperatures of thousands of degrees, the carbon-hydrogen bonds in methane molecules may break apart, the carbon atoms becoming separated from their hydrogen atoms. Under high enough pressure, carbon forms diamond. Some theoretical models suggest that deep inside Neptune's mantle, where the conditions are right, carbon atoms dissociated from methane might crystallize into diamonds. Tiny, hard, dense particles that would then sink slowly toward the core under gravity, releasing energy as they fall and contributing to Neptune's observed excess heat output. This is a genuinely extraordinary idea. It rains diamonds inside Neptune, not as an occasional event, but as an ongoing, continuous process, with carbon crystallizing in the deep mantle and drifting downward toward the core. An eternal diamond rain in a world we have visited only once, briefly, decades ago. Experimental work using laser-driven shock compression of plastic materials, a proxy for the methane in Neptune's interior, has actually produced results consistent with diamond formation under the relevant conditions, lending some empirical support to the theoretical models. One set of experiments at the Stanford Linear Accelerator Center used extremely powerful laser pulses to shock compressed plastic, effectively recreating pressure-temperature conditions similar to those expected in Neptune's interior, and found that diamond-like carbon structures formed on timescales of billionths of a second. The diamond rain hypothesis is not confirmed. It is a theoretical prediction based on incomplete models of the interior, but it is taken seriously as a plausible feature of Neptune's deep interior. The comparison between Neptune and Uranus is worth pausing on, because despite their broad compositional similarities, the two ice giants are strikingly different in one crucial way: their internal heat. Uranus radiates almost exactly as much energy as it receives from the sun. Its internal heat source is essentially zero, or at least undetectable with current measurements. Neptune, by contrast, radiates about 2.5 times more energy than it receives. This discrepancy between two otherwise similar planets is one of the most puzzling, unresolved questions in planetary science. One hypothesis is that Uranus's interior is thermally stratified in a way that prevents its internal heat from escaping. If there is a compositional or density gradient in Uranus's interior that inhibits convection in the main part of the mantle, heat could be trapped there rather than being transported to the surface and radiated away. Neptune, lacking such a stratification, would convect more freely and release its heat more efficiently. This explanation is appealing in its simplicity, but it requires specific details about the interior compositions of both planets that we cannot yet measure directly. Another hypothesis involves the impact history of the planets. Uranus's dramatic axial tilt, it rotates nearly on its side, tilted at about 98 degrees, is almost certainly the result of a large impact during the early solar system. Some models suggest that a sufficiently energetic impact could have disrupted Uranus's internal structure in a way that inhibited convection and trapped heat, while Neptune, which experienced no comparable impact, retained a more normal convective structure. But this explanation also requires assumptions about interior structures that are difficult to verify. The mystery of the heat difference between Uranus and Neptune is one of the primary scientific motivations for sending orbiters to both planets. Observations from orbit could constrain their interior structures far better than current Earth-based and telescope observations, and might resolve a question that has puzzled planetary scientists for decades. The deep interior of Neptune is one of the places where ordinary language begins to fail. We can say water, ammonia, and methane, but those words bring to mind familiar substances: liquid water in a glass, ammonia as a sharp-smelling gas, methane as a simple molecule associated with natural gas. Inside Neptune, these materials are crushed and heated into states that have little in common with their everyday forms. The pressure rises to millions of times the pressure at Earth's surface. Temperatures reach thousands of degrees. Molecules can break apart. Ions can move freely. A substance that would be ice in the outer solar system can behave like a hot, dense, electrically conducting fluid. This is why the term ice giant is both useful and confusing. It is useful because planetary scientists use ices to refer to volatile compounds such as water, methane, and ammonia, materials that froze easily in the cold outer solar nebula. It is confusing because Neptune is not a giant ball of frozen ice. It is a planet dominated by materials that began as ices during formation but are now mostly in high-pressure fluid states deep inside the planet. Some models divide Neptune into an outer hydrogen-helium envelope, a vast mantle rich in water, ammonia, and methane, and a small rocky core. But the boundaries between these regions may not be sharp. They may blend gradually, with composition changing over depth rather than shifting abruptly from one layer to another. This uncertainty matters because the way heat moves through the interior depends on whether the planet is well mixed or stratified. If convection carries heat efficiently upward, the planet can radiate internal heat strongly. If compositional layers suppress convection, heat can become trapped. The mystery of Neptune's heat is therefore connected to the mystery of its interior layering. Neptune emits far more energy than it receives from the Sun Uranus. Its near twin in size and composition does not. Why? The answer could involve formation history, giant impacts, different internal structures, different degrees of layering, or different efficiencies of convection. Without an orbiter, and ideally without atmospheric probes, we cannot yet choose confidently between those possibilities. This is not a minor detail. Ice giants appear to be common in the galaxy, and sub-Neptune exoplanets are among the most frequently detected planets around other stars. If we do not understand how Neptune stores and releases heat, how its mantle convects, how its magnetic field is generated, and how its atmosphere connects to the deep interior, then we are missing a major piece of planetary science. Neptune is not an exotic exception. It may be a local representative of an extremely common kind of world. Neptune's magnetic field is another source of genuine strangeness, and it adds to the picture of a planet whose interior physics we only partially understand. Earth's magnetic field is generated by the convection of liquid iron in the outer core, and it is relatively well aligned with the rotation axis. Earth's magnetic north is within about 11 degrees of geographic north. Jupiter's magnetic field is about 10 degrees offset from its axis. Most planetary magnetic fields are roughly aligned with the rotation axis, within about 20 or 30 degrees. Neptune's magnetic field is tilted about 47 degrees from its rotation axis, nearly half a right angle. And it is not just tilted but offset, meaning the center of the magnetic dipole is not at the center of the planet, but displaced by about 13,500 kilometers from the planet's geometric center, roughly halfway to the cloud tops. This is one of the most dramatically offset and tilted magnetic fields in the solar system. The result is a magnetic field that wobbles dramatically as Neptune rotates. Rather than sweeping consistently around the planet, it tilts and rocks in a way that creates a complex, asymmetric magnetosphere. This unusual magnetic configuration is believed to result from the location of the field-generating region within Neptune's interior. On Earth, the magnetic dynamo operates deep in the liquid iron outer core. On Neptune, the high-pressure, electrically conducting water-ammonia fluid in the mantle, not a deep core, may be the primary location of the dynamo generating the magnetic field. A dynamo operating in the mantle, where convection patterns are more complex and the flow more turbulent and irregular, would naturally produce a more complex, offset, tilted field than the deeper dynamos of gas giant planets. If this model is correct, Neptune's strange magnetic field is a direct expression of the unusual nature of its interior, a mantle of hot, compressed, conducting water and ammonia, generating magnetism in a different way from anything we find in the terrestrial planets or the gas giants. Uranus shares this peculiarity. Its magnetic field is also dramatically tilted and offset, suggesting that both ice giants have their dynamos in their mantles rather than in their cores. This is one of the defining characteristics that distinguishes ice giants from gas giants in terms of their deep interior physics. And it's one of the reasons that studying the ice giants more closely is considered so valuable. They represent a class of planetary interior that is not well represented anywhere else in the solar system, and that may be among the most common types of planet in the universe at large. Neptune's magnetosphere would look strange even compared with the already strange magnetic environments of the outer planets. Because the magnetic field is both tilted and offset, the region controlled by that field does not rotate smoothly around the planet in a simple symmetric way. As Neptune spins every 16 hours, the magnetic field sweeps through space like a tilted, off-center lighthouse beam. Charged particles trapped in the magnetosphere experience changing field strengths and changing geometry. The solar wind, flowing outward from the sun, presses against a magnetic obstacle that changes shape and orientation during each rotation. This makes Neptune's auroras and charged particle environment difficult to predict. On Earth, auroras occur near the magnetic poles, which are offset from the geographic poles but still relatively close. On Neptune, the magnetic poles wander far from the rotation poles as the planet turns. Any auroral emissions would not form the simple oval patterns familiar from Earth. They would shift, tilt, and migrate with the rotating magnetic field, producing a complicated interaction between the planet's atmosphere, its magnetosphere, and the solar wind. The magnetosphere also interacts with Triton and the other moons. Triton's thin atmosphere and ionosphere may exchange particles with Neptune's magnetic environment. Dust from the rings and small moons can become charged and shaped by electromagnetic forces. The entire region around Neptune is therefore not empty space with a planet in the middle. It is a dynamic plasma environment, thin by human standards but scientifically rich, where particles, fields, moons, rings, and sunlight all interact. Voyager 2 measured this environment only briefly. It passed through once, along one trajectory, at one moment in Neptune's long seasonal cycle. That is enough to reveal the field's basic strangeness, but not enough to understand its full behavior. An orbiter would change everything. By circling Neptune over months or years, it could map the magnetic field from different angles, observe how the magnetosphere responds to the solar wind, study how Triton interacts with the field, and test models of ice giant dynamos directly. In that sense, Neptune's magnetic field is not just a feature of the planet. It is a diagnostic tool. It is a clue coming from deep inside the ice giant, written in invisible lines of force extending far into space. Neptune has rings. They are faint, dark, and narrow, completely invisible from Earth without specialized instruments. Discovered by Voyager 2 during its 1989 flyby, though some evidence for their existence had been gathered by ground-based observations in the years before. There are 5 main rings, named after astronomers associated with Neptune's discovery and study: Gal, Leverrier, Lassell, Arago, and Adams. The outermost ring, Adams, is the most prominent and the most unusual. Unlike Saturn's broad, continuous ring bands, the Adams ring is not uniform around its circumference. Instead, it has 5 brighter, denser arcs, called Fraternité, Égalité 1, Égalité 2, Liberté, and Courage, that occupy specific angular positions in the ring and are separated by more diffuse material. These arcs are remarkable because they should not persist. Collisions between ring particles, which naturally spread material over time, should have smoothed out any concentration in the ring and distributed the arc's material evenly around the ring over timescales of centuries. The fact that the arcs still exist suggests they are being actively maintained by the gravitational influence of a nearby moon, which creates resonance effects that confine the material. The moon responsible appears to be Galatea, a small, irregularly shaped moon orbiting just inside the atom's ring, whose orbital period is in a 42 to 43 resonance with the ring material in the arcs. This resonance creates a pattern of gravitational nudges that pushes ring particles toward the arc locations and away from the gaps between arcs, maintaining the clumped structure against the natural tendency of collisions to spread it out. The precise mechanism is complex, and the stability of the arcs over long timescales is still being studied theoretically. Some models suggest the arcs are gradually dispersing and might disappear over timescales of centuries, while others suggest Galatea's resonance is strong enough to maintain them indefinitely. The rings are made of dark, carbonaceous material, dark enough to have a very low albedo, reflecting only a few % of the light that hits them. This dark material is similar in character to the surfaces of dark, primitive asteroids and to the material found in Kuiper belt objects, consistent with the idea that much of Neptune's ring material has a composition reflecting the outer solar system environment where it formed or was captured. The rings are less massive and less visually striking than Saturn's, less extensive even than Jupiter's in some ways, and their study from Earth-based observations, even with the best telescopes, remains difficult. Much of what we know about them comes from Voyager 2's brief passage through the system, supplemented by painstaking work with large ground-based telescopes and the Hubble Space Telescope. Neptune's rings also remind us that ring systems do not have to resemble Saturn's to be scientifically important. Saturn's rings are bright, broad, and made mostly of reflective water ice. They dominate the visual identity of the planet. Neptune's rings are the opposite: dark, narrow, faint, and difficult to see. If Saturn's rings are a shining disk of frost, Neptune's are more like smoke drawn into thin gravitational threads. They reflect little light. They are sparse. They do not announce themselves to casual observation, but their faintness makes them interesting. Dark rings contain clues about the material environment of the outer solar system. Their particles may be coated with radiation-processed organics, carbon-rich dust, or materials similar to the dark surfaces of small Kuiper belt objects. Their arcs are especially valuable because they show that a ring can be incomplete and still persist, at least for some time, if gravitational resonances confine the particles. The atom's ring arcs are one of those features that seem almost too delicate to survive. Ring particles orbit quickly. Collisions should spread clumps into a uniform band. Tiny gravitational tugs from nearby moons should disturb the structure. Radiation forces and micrometeoroid impacts should slowly erode the material. And yet the arcs are there, brighter than their surroundings, arranged in persistent concentrations. A future Neptune orbiter could watch those arcs over time. It could measure whether they are stable, drifting, weakening, or being replenished. It could map the sizes of particles, the composition of the dark material, and the gravitational influence of Galatea in far more detail than Voyager 2 could. It could also search for small embedded moons or moonlets that may be helping maintain the arcs in ways we have not yet resolved. Small ring systems matter because they reveal the same physics as large ones, but in a more fragile form. Collisions, resonances, shepherding, dust production, electromagnetic forces, and moon-ring interactions all operate at Neptune, just as they do at Saturn, but with different materials and far less mass. Studying them helps us understand not only Neptune, but the general behavior of disks, from planetary rings to debris disks around stars to the early disks from which planets form. No discussion of Neptune can proceed very far without arriving at Triton, the planet's largest moon, and one of the most remarkable objects in the entire solar system. Triton stands alone in many ways. A moon that doesn't belong where it is, a moon that is slowly approaching its own destruction, a moon with active geology powered by a mechanism quite unlike any other moon we've studied closely. Triton is large, about 70% the diameter of our moon, making it the seventh largest moon in the solar system. It is dense, with a surface of nitrogen ice and frozen carbon dioxide over a presumed rocky interior. Its surface temperature, measured by Voyager 2 during the flyby, is approximately -235 degrees Celsius, making it one of the coldest surfaces ever measured by a spacecraft in the solar system. Only about 38 degrees above absolute zero, the theoretical minimum temperature at which all molecular motion ceases. The most immediately striking thing about Triton is its orbit. Every other large moon in the solar system orbits its parent planet in the same direction the planet rotates. The result of both the planet and its moons having formed from the same rotating disk of material, all naturally turning in the same direction. Triton orbits Neptune backwards. It moves in the direction opposite to Neptune's rotation in what's called a retrograde orbit, inclined at about 23 degrees to Neptune's equatorial plane. This retrograde orbit is almost impossible to explain if Triton formed alongside Neptune. The only credible explanation is that Triton didn't form alongside Neptune at all. It formed somewhere else, in the Kuiper Belt, the vast disk of icy objects beyond Neptune's orbit, and was captured by Neptune's gravity at some point in the distant past. The capture of an object as large as Triton is not a trivial event. A Kuiper Belt object approaching Neptune would normally fly past on a hyperbolic trajectory, its speed too great for Neptune's gravity to hold it. For capture to occur, the incoming object needs to lose energy in some way, either through interaction with gas drag in a denser early solar system, or through a three-body interaction, where the incoming object interacted gravitationally with another body at the right moment, transferring enough energy to allow Neptune to hold it. Some models suggest that Triton may originally have been part of a binary Kuiper Belt pair, two objects orbiting each other, and that the binary's interaction with Neptune's gravity led to the capture of one while the other was ejected. The capture of Triton would have been a catastrophic event for Neptune's original moon system. A large object arriving on a retrograde trajectory would have tidally disrupted, scattered, or ejected many or all of the moons that existed in Neptune's system at the time. The small, irregularly shaped moons of Neptune's outer system are thought by some models to be remnant debris from that catastrophe, fragments of moons that were broken apart or flung into new orbits during the violent period following Triton's arrival. The inner, regular moons closer to Neptune may have reformed from debris in the aftermath, explaining why they are smaller and more irregularly shaped than the major moons of Jupiter, Saturn, or Uranus. Once captured in a retrograde orbit, Triton's fate was determined by tidal interaction with Neptune. Because Triton orbits in the opposite direction to Neptune's rotation, the tidal bulge that Neptune raises in Triton is positioned on the wrong side of the direction of motion, draining orbital energy from Triton rather than adding it, as tides normally do for prograde moons. This means Triton is spiraling inward, slowly but steadily, losing orbital energy to tidal friction, moving a little closer to Neptune with every orbit. In approximately 3.5 billion years, Triton will cross Neptune's Roche limit and be torn apart by tidal forces, its material spreading into a ring system around Neptune that would rival Saturn's rings in extent and visual splendor. though no one will be here to see it, given the timescales involved. For now, Triton orbits at a distance of about 354,000 kilometers from Neptune, slightly farther than Earth's moon is from Earth, completing one retrograde orbit every 5.9 Earth days. What Voyager 2 found when it arrived at Triton in 1989 was more extraordinary than many scientists had anticipated. The moon has a very young surface by geological standards, not the ancient, cratered terrain of old, dead worlds like Earth's moon or Mars's Phobos. Triton's surface showed relatively few impact craters, suggesting it has been geologically active recently, and its surface is periodically resurfaced. And it showed direct evidence of ongoing geological activity, geysers. Active geysers erupting from Triton's south polar cap, shooting dark plumes of nitrogen gas and fine particles upwards several kilometers above the surface, before the plumes were deflected by Triton's thin nitrogen atmosphere and stretched out into dark streamers that stretched hundreds of kilometers downwind. Voyager 2 photographed several of these geysers in operation, producing some of the most extraordinary images from the mission: dark, thin plumes rising from a frozen nitrogen surface at the most distant moon ever photographed by a visiting spacecraft. The geysers are not powered by internal heat from below, the way geysers on Earth or the plumes of Enceladus are. Instead, Triton's geysers appear to be driven by a solar heating mechanism, a kind of natural greenhouse effect operating in the transparent nitrogen ice of the polar cap. Solar radiation, though extremely weak at Neptune's distance, penetrates the transparent nitrogen ice surface and is absorbed by the darker material beneath. The trapped heat converts some of the solid nitrogen ice to gas, building up pressure beneath the ice until it erupts upward through weak points in the surface, carrying dark material with it and depositing it in long, downwind streamers across the polar terrain. The surface of Triton itself is remarkable in its variety. The southern polar region, near where the geysers were observed, shows a pinkish-brown tint to its nitrogen ice, likely from the presence of organic compounds formed by radiation chemistry in the upper layers of the polar cap. Other regions show a terrain sometimes called cantaloupe terrain, a distinctive surface covered in pits and domes arranged in a regular pattern reminiscent of the skin of a cantaloupe melon. This unusual terrain, unique in the solar system, may be the result of convective overturn in the icy crust, with warmer, less dense ice rising and cooler, denser ice sinking, in a frozen equivalent of the convection that drives mantle circulation on Earth. The presence of such terrain suggests Triton's interior may have been, or may still be, warm enough for ice to slowly deform and circulate on geological timescales. There are also regions of what appear to be frozen lava flows or ice volcanic features, cryovolcanic landforms where water ammonia slush may have erupted from the interior in the geological past, spreading across the surface and freezing into the smooth plains visible today. Triton may harbor a subsurface ocean of liquid water, similar to Europa and Enceladus, maintained by tidal heating from Neptune. The tidal heating that is gradually drawing Triton's orbit inward also generates internal heat in Triton's interior, and models suggest this heat could be sufficient to maintain liquid water at depth. If true, Triton, a captured Kuiper Belt object, in retrograde orbit around Neptune, with active surface geysers and possible internal ocean, is another candidate for the category of ocean worlds that increasingly appears to be surprisingly common in the outer solar system. Triton has a thin atmosphere, composed primarily of nitrogen with traces of carbon monoxide and methane. The atmospheric pressure at the surface is roughly 14 microbars, about 70,000 times less than Earth's atmospheric pressure. This atmosphere is so thin as to be essentially invisible and provides no protection from radiation or significant insulation against the cold. And yet it is dynamic. Triton's atmosphere changes subtly with the season, as nitrogen ice evaporates from one polar region and is deposited on the other, slightly changing the atmospheric density as the polar caps exchange mass over the course of Triton's long seasonal cycle. Triton's capture may have been one of the most violent events in the history of any giant planet's moon system. Before Triton arrived, Neptune likely had a more ordinary set of moons, perhaps formed from a disk around the young planet, orbiting in the same direction as Neptune's rotation. Then Triton, probably born in the Kuiper belt, entered the system. To be captured, it had to lose orbital energy. The binary capture model provides one elegant possibility. Triton may once have had a companion. As the binary pair passed close to Neptune, the planet's gravity separated the two objects. One was flung away with extra energy. The other, Triton, lost enough energy to remain bound to Neptune. That kind of event would not leave the existing system undisturbed. A newly captured Triton would have had an elongated, inclined, probably chaotic orbit at first. Over time, tides raised by Neptune would have circularized Triton's orbit, converting orbital energy into heat. During that long settling period, Triton would have crossed the orbits of any pre-existing moons, scattering them, colliding with them, or ejecting them. The small inner moons we see today may be second-generation bodies, assembled from debris after the original system was disrupted. This makes Triton more than a moon. It is evidence of a captured past. It is a Kuiper belt object now trapped in orbit around a giant planet, carrying information about the outer solar system into the Neptunian system. If we could study Triton's surface composition in detail, map its geology globally, measure its interior, and sample its thin atmosphere, we would not only learn about Triton. We would learn about the same population of icy bodies that includes Pluto, Eris, Makemake, and countless smaller worlds beyond Neptune. Triton's possible ocean adds another layer of importance. If liquid water exists beneath the surface, then Triton joins the growing list of ocean worlds in the outer solar system. It would be different from Europa because it is colder and farther from the Sun, different from Enceladus because its plume mechanism may not expose ocean material directly, different from Titan because its surface chemistry and atmosphere are thinner. But the broader pattern would remain. Liquid water may be much more common in the outer solar system than earlier generations of scientists expected. The eventual destruction of Triton is a reminder that moon systems evolve. Triton's retrograde orbit causes tidal interactions that slowly pull it inward. The timescale is enormous, measured in billions of years, but the direction is clear. One day, if the system remains undisturbed, Triton will approach Neptune closely enough that tidal forces overcome its self-gravity. It will break apart. Its fragments will spread into rings. Neptune may become, for a time, a spectacular ringed planet. That future ring system would be born from the destruction of a captured world. It is a distant echo of Saturn's possible ring origin, a reminder that beauty in planetary systems often comes from disruption. Rings are not always decorations. Sometimes they are ruins, arranged by gravity into elegance. Neptune has 16 known moons, and the moons beyond Triton are far less dramatic than Triton, but collectively tell an interesting story about the system's complex history. Nereid is the third largest Neptunian moon, discovered in 1949 by Gerard Kuiper, the astronomer whose name is associated with the belt of icy objects beyond Neptune. Nereid has an extraordinarily eccentric orbit, the most eccentric of any known moon in the solar system. At its closest approach to Neptune, it comes within about 1.5 million kilometers, while at its farthest it retreats to about 9.5 million kilometers. This extreme eccentricity is thought to be the result of gravitational perturbation during Triton's capture, a moon that was formerly on a more circular orbit. kicked into its current wild orbit by the gravitational chaos that followed Triton's arrival. The inner moons of Neptune, Naiad, Thalassa, Despina, Galatea, Larissa, Hippocamp, and Proteus, are all small, irregularly shaped objects, orbiting in prograde, roughly circular orbits close to Neptune. They are dark, with low reflectivities consistent with carbonaceous composition. Several of them are embedded within or near the ring system and play roles in shaping the ring's structure, as we discussed with Galatea and the Adam's ring arcs. These moons are thought to be relatively young, possibly having reformed from debris after Triton's capture disrupted any earlier moon system, and their irregular, non-spherical shapes are consistent with objects that haven't undergone the gravitational compression into spherical form that larger, more massive moons achieve. Proteus, the largest of the inner regular moons at about 420 kilometers in longest dimension, was actually larger than Nereid but wasn't discovered until Voyager 2's flyby in 1989 because it orbits so close to Neptune and reflects so little light that Earth-based telescopes could not resolve it against the planet's brightness. Voyager 2 revealed it as a heavily cratered, boxy, dark body, the kind of object that, in a quieter solar system environment, might have continued accumulating material and grown into a larger, rounder moon, but in Neptune's dynamically disrupted system remained as a modest, irregular survivor. Hippocamp, one of Neptune's small inner moons, was found in 2013 from analysis of archival Hubble images, a tiny moon, only about 34 kilometers across, orbiting very close to Proteus. Its discovery was notable not just for adding another moon to the count, but for suggesting that it may be a fragment broken off Proteus by an ancient impact, potentially providing a clue about the history of impacts and collisions in the inner Neptunian system. Beyond the inner regular moons and Nereid, Neptune has a population of small, irregular outer moons in distant, inclined, often retrograde orbits, likely captured objects from the Kuiper belt, similar to the irregular moons of Jupiter and Saturn. These distant moons are known mostly as points of light in telescope images, their surfaces and compositions almost entirely unknown, waiting for a future mission to study them more closely. Now let's talk about the only time humanity has ever visited Neptune up close, the Voyager 2 flyby of August 25, 1989, because it is a story worth telling slowly and with the attention it deserves. Voyager 2 was launched in August 1977, 12 years before its Neptune encounter. It made its closest approach to Jupiter in 1979, then used Jupiter's gravity to accelerate towards Saturn, arriving in 1981. Saturn's gravity then redirected it toward Uranus, which it reached in January 1986. And Uranus's gravity was used in turn to redirect Voyager 2 toward Neptune, the final planetary destination in what NASA called the Grand Tour, a once-in-175-year planetary alignment that made it possible for a single spacecraft to visit all 4 outer planets using successive gravitational assists, an alignment that no one alive today will see again. The Grand Tour opportunity was identified in the late 1960s by a young engineer named Gary Flandreau, working at the Jet Propulsion Laboratory, who calculated that the alignment of Jupiter, Saturn, Uranus, and Neptune in the late 1970s would allow a spacecraft launched in that window to visit all 4 planets using the gravity of each one to accelerate toward the next. Without this alignment, visiting all 4 planets would have required either decades of additional travel time or propulsion systems far beyond anything available. With it, the journey could be completed in roughly 12 years, a once-in-almost 2 centuries opportunity that the planetary science community was determined not to miss. By the time Voyager 2 reached Neptune, it had been traveling for 12 years. The teams of scientists and engineers who launched it were 12 years older. Some of the youngest mission controllers at launch were now senior scientists. The spacecraft itself was the product of 1970s technology, launched before personal computers were common, before the internet existed, before most of the digital tools that define modern scientific work had been developed. And it was still working. Its instruments still functioning, its power declining but sufficient, its antenna still precisely aimed at Earth across 4.5 billion kilometers of space, its operating system still responding to commands sent from Earth 4 hours and 6 minutes earlier. Managing Voyager 2 at Neptune's distance required extraordinary precision. Commands sent to the spacecraft were based on predictions of where it would be and what conditions it would encounter. Predictions made months and years in advance, with corrections possible only within the long constraints of the communication delay. The observation sequence was designed to capture the maximum scientific return from the limited encounter time. Cameras pointing here, instruments measuring that, the timing of each observation calibrated to within seconds across a planning timeline months in the making. The flyby itself lasted only about 5 hours at closest approach. Closest approach to Neptune occurred on August 25, 1989, when Voyager 2 passed within about 4,900 kilometers of the planet's cloud tops, closer than it had come to any of the other planets it had visited. The spacecraft then swung around to make a close pass of Triton approximately 5 hours later. In those few hours, Voyager 2 photographed the Great Dark Spot in detail, discovered the ring arcs of the Adam's ring, mapped Triton's surface in the best resolution ever achieved, detected the geysers of Triton erupting from the south polar cap, measured wind speeds in Neptune's atmosphere that no one had anticipated being so extreme, characterized the magnetic field, and found it dramatically tilted 47 degrees from the rotation axis, discovered 6 new moons, measured the temperature and composition of the upper atmosphere, and gathered the kind of fundamental, irreplaceable data that transformed Neptune from a faint telescopic smudge into a world we could study scientifically. The images were delayed in reaching Earth by the immense distance. Radio signals traveling at the speed of light still took 4 hours and 6 minutes to cross the 4.5 billion kilometers between Neptune and Earth. The scientists and engineers who watched those images come in, slowly resolving pixel by pixel on monitors and mission control at the Jet Propulsion Laboratory, knew they were seeing things no human had ever seen before. A planet's cloud storms photographed from nearby, a captured moon's geysers captured mid-eruption, a ring system's clumped arcs revealed for the first time, and that they were receiving that information from a spacecraft that had been traveling for 12 years to deliver it. There is something deeply moving about the Voyager 2 Neptune encounter, considered at a distance of more than 30 years. A spacecraft the size of a large car, built with 1970s technology, launched before home computers existed, had traveled billions of kilometers through the outer solar system, navigated a precisely calculated gravitational course past 4 planets, and was now sending back detailed scientific data on a world that human beings had never before seen up close. The entire enterprise represents something remarkable about what human beings are capable of when they commit to a long, careful, patient goal, when they decide that something matters enough to plan for it 12 years in advance and follow through. After the Neptune flyby, Voyager 2 continued on a trajectory taking it out of the solar system entirely, angled below the plane of the solar system. It is now in interstellar space, having crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in 2018, 29 years after its Neptune encounter. It continues to transmit faint signals back to Earth, its power slowly diminishing as its plutonium power source decays, its distance increasing by approximately 3 kilometers every second. It carries a golden record of Earth's sounds and images, and it will drift through interstellar space for billions of years after its instruments fall silent, carrying that record toward no particular destination, a small, slow message from a species that wanted the universe to know it had been here. There has been no return to Neptune since 1989. No orbiter, no atmospheric probe, no lander on Triton. More than 3.5 decades have passed, and Neptune has received no visitors. The planetary science community has consistently ranked an ice giant mission as a top priority. The scientific case is compelling. An orbiter at Neptune could study the planet's interior and magnetic field in detail, monitor its atmospheric dynamics over years, make repeated close passes of Triton to study its geysers and possible subsurface ocean, characterize the rings and inner moons, and transform our understanding of ice giant planets more broadly. The challenge is fundamentally one of cost, travel time, and mission architecture, with Neptune's extreme distance making any mission there an investment of over a decade just in transit. A Neptune orbiter would be one of the most scientifically valuable missions still missing from our exploration of the outer solar system. Such a mission would not merely take better photographs. It would answer basic questions that cannot be answered from Earth. It could measure Neptune's gravity field precisely, revealing how mass is distributed inside the planet. It could map the magnetic field over many rotations, testing whether the dynamo models for ice giants are correct. It could monitor atmospheric storms over months or years rather than hours, separating short-lived weather from long-term seasonal changes. It could observe the rings repeatedly, watching their arcs and dust structures evolve. It could fly by Triton many times, mapping its surface, measuring its atmosphere, and searching for evidence of a subsurface ocean. An atmospheric probe would be especially powerful. The noble gases in a planet's atmosphere, helium, neon, argon, krypton, xenon, are chemically quiet. They do not easily react, which means their abundance ratios can preserve information about where and how the planet formed. Measuring those gases in Neptune's atmosphere would help scientists test models of the early solar nebula. A probe could also measure isotopes, methane abundance, cloud layers, temperature, pressure, and winds as it descended. These data would improve not only our understanding of Neptune, but also our models of Uranus and exoplanets. The difficulty is distance. Neptune is far enough away that every mission becomes a long commitment. A launch in the right window might still require more than a decade of travel. Power is difficult because sunlight is so weak, solar panels become impractical, so radioisotope power is usually required. Communication is slow because signals take hours to cross the distance. Mission design must account for gravity assists, long cruise phases, and the need for spacecraft systems to survive for many years before the main science even begins. This is why no Neptune orbiter has yet flown. Not because Neptune is unimportant, but because exploring it properly is hard. It requires patience across political, financial, and scientific timescales. It requires people to begin a mission knowing that the most important data may arrive when they are much older, or perhaps after some of the original team has retired. In that sense, a Neptune mission would be very much in the spirit of Neptune itself: slow, distant, and worth waiting for. It is also worth thinking about how little of Neptune we have truly measured directly. A spacecraft flyby is incredibly valuable, but it is still a flyby. Voyager 2 passed through the Neptune system once, along a single path, at a single season, during a few intense hours of close observation. Imagine trying to understand Earth from one airplane flight over one hemisphere on one day. You might see clouds, storms, mountains, coastlines, deserts, and oceans. You might collect useful data, but you would not know the climate. You would not know the seasonal cycles. You would not know how storms begin and end across years. You would not know how the deep ocean connects to the atmosphere, or how the magnetic field behaves over long times. That is roughly the situation with Neptune. Voyager 2 gave us the first close truth. Hubble, the James Webb Space Telescope, Keck, the Very Large Telescope, and other observatories have extended that truth across decades. They have tracked storms, clouds, hazes, thermal changes, and dark vortices. They have improved our understanding enormously, but they remain distant observers, studying a small blue disk billions of kilometers away. An orbiter changes the kind of science possible. It transforms a planet from an encounter into an environment. Instead of asking what Neptune looked like during one flyby, scientists could ask how its atmosphere evolves over a season, how its magnetic field changes with solar wind conditions, how ring arcs drift over time, how Triton's atmosphere responds to changing sunlight, and how small moons interact with dust and plasma. Repeated close passes build a time series. A time series turns snapshots into physics. This is why the absence of a Neptune orbiter is so noticeable. We have orbited Jupiter with Galileo and Juno. We orbited Saturn with Cassini for 13 years. We have orbited Mars many times. Neptune, by comparison, remains a planet known mostly from a single close look and many distant glances. It is not neglected because it is uninteresting. It is neglected because it is difficult to reach, difficult to power, difficult to communicate with, and expensive to study properly. But difficulty is not the same as impossibility. The history of space exploration is full of missions that seemed unreasonable until they became real. Voyager itself was built around a rare alignment and a willingness to commit to a journey that would take more than a decade. A future Neptune mission would require that same kind of patience. Mission studies have repeatedly noted that launch windows using Jupiter gravity assists can make ice giant missions more practical, but no dedicated Neptune orbiter has yet been approved. Whether a future Neptune mission is selected will be decided not only by physics, but by budgets, priorities, spacecraft power systems, and the long patience required for any journey to the outer solar system. For now, Neptune waits. Patient, blue, remote, windswept, still holding most of its secrets from the single brief visit it received in the summer of 1989. Neptune's role in shaping the outer solar system is far larger than its relative neglect in popular science might suggest. Neptune is, in many ways, the gravitational gatekeeper of the outer solar system, the outermost true giant, whose gravity has been sculpting the distribution of smaller bodies in the Kuiper Belt and beyond for the entirety of the solar system's history. The Kuiper Belt, the vast disk of icy objects that extends from roughly 30 to 50 astronomical units from the Sun, from Neptune's orbit outward, is not uniformly distributed. It is organized, and Neptune's gravity is largely responsible for that organization. Just as Jupiter's gravity sculpts the asteroid belt between Mars and Jupiter, creating gaps and concentrations through orbital resonances, Neptune's gravity has organized the Kuiper Belt into distinct populations defined by their orbital relationships to Neptune. The most prominent of these resonant populations is the Plutinos, a large class of Kuiper Belt objects, including Pluto itself, that are in a 2 to 3 orbital resonance with Neptune. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance has been protecting Pluto from close gravitational encounters with Neptune for billions of years, keeping its orbit stable despite the fact that Pluto's orbit crosses inside Neptune's for part of each orbit. The resonance ensures that whenever Pluto crosses into Neptune's orbital neighborhood, Neptune is always safely on the other side of the Sun, their paths repeatedly synchronized to avoid any dangerous approach. The classical Kuiper Belt, the cold population of objects with nearly circular orbits in the 39 to 48 astronomical unit range, is thought to represent objects that largely formed in place and were not significantly scattered by Neptune's gravity. The hot population, with more eccentric and more inclined orbits, is thought to have been scattered into its current configuration by gravitational interactions with Neptune during the early solar system, when the giant planets were still migrating to their current positions. The nice model of early solar system evolution, named after the city in France where it was developed, proposes that the giant planets did not form in their current positions but migrated over the first few 100 million years of solar system history. In this model, Jupiter, Saturn, Uranus, and Neptune all formed somewhat closer to the Sun than they orbit today, in a more compact configuration, and then migrated outward as they interacted gravitationally with the vast disk of planetesimals that filled the outer solar system in its early history. Neptune, in particular, is thought to have migrated outward significantly, sweeping up and scattering much of the primordial Kuiper belt as it did so, and in the process sending a pulse of objects inward, the late heavy bombardment that cratered the Moon, Mars, and Earth in their early histories. If the nice model or its descendants are broadly correct, then Neptune's current position is not where it started. The planet migrated to its present orbit, and in doing so, it reorganized the outer solar system, scattered much of the primordial Kuiper belt, and delivered a significant bombardment to the inner solar system. Neptune's gravity has been one of the dominant forces shaping the distribution of material throughout the outer solar system for most of the solar system's history. Beyond the Kuiper belt, Neptune's gravity still influences the distant outer solar system. The scattered disk, a population of objects with highly eccentric orbits that bring them close to Neptune's orbit at perihelion, was created by Neptune's gravitational scattering, and its members continue to interact with Neptune over billions of year timescales. Even further out, in the inner Oort cloud and possibly the outer Oort cloud, the cumulative effect of Neptune's gravity over solar system history has contributed to the distribution of objects in ways that are still being studied and modeled. Neptune is, in short, not just a destination at the edge of the known solar system. It is one of the primary architects of the solar system's current large-scale structure. Its gravity has been at work for over 4 billion years, quietly organizing, scattering, and sculpting the arrangement of objects throughout the outer solar system in ways that still affect everything from the rate of cometary impacts on Earth to the distribution of trans-Neptunian objects in the Kuiper belt. Let's step back now and think about what Neptune tells us about the universe beyond our solar system, because that connection turns out to be particularly important. For most of astronomy's history, the solar system was the only planetary system we knew. We could see Jupiter and Saturn and Neptune in detail, and we could look at other stars, but the planets around those other stars were far too faint, far too close to their blazing host stars, to be directly detected. All of our knowledge of planetary diversity came from the 8 planets of our own system. Since the 1990s, and accelerating dramatically with the Kepler Space Telescope and its successors, we have discovered thousands of planets orbiting other stars. And one of the most significant findings from that survey of exoplanets is the prevalence of a type of planet that doesn't have a close analog in our solar system: the subneptune or mini-Neptune, a planet with a mass of roughly 1 to 4 times Earth's mass and a substantial hydrogen-rich atmosphere, intermediate between the rocky terrestrial planets and the ice giants like Neptune. These subneptunes are extraordinarily common. They appear to be the most common type of planet in the Milky Way, at least at the orbital distances accessible to current detection methods. Our solar system has none. The smallest planet in our solar system with a significant atmosphere is Venus, and the smallest giant planet is Neptune, with nothing in between. But around other stars, the gap our solar system has between rocky planets and ice giants is filled by a whole population of worlds that we don't have a local representative of to study up close. This makes Neptune, as the closest thing we have to the smaller end of the ice giant class, particularly valuable as a reference point for understanding this most common category of exoplanet. Understanding Neptune's interior, its atmospheric composition, its magnetic field, and its weather patterns can help calibrate the models we use to interpret the meager data we have on distant sub-Neptune exoplanets. In a very real sense, studying Neptune is studying the most common type of planet in the galaxy, just from a somewhat large representative of the class. The interior composition of ice giants, that mixture of water, ammonia, and methane under high pressure, may be a very common type of planetary interior in the galaxy. The equations of state for water-ammonia mixtures under extreme pressure, the behavior of conducting fluids in these conditions, the generation of magnetic fields by mantle dynamos rather than core dynamos. All of these are relevant not just to Neptune and Uranus, but to the enormous population of sub-Neptune planets we are discovering around other stars. Every insight gained from a better understanding of Neptune's interior contributes to our ability to interpret the nature of worlds far beyond our solar system. Let's also pause to consider what it actually means for Neptune to have existed, largely unknown and unstudied, through the entirety of human civilization up until the mid-19th century. Neptune has been orbiting the Sun for 4.5 billion years. Throughout the entire span of human existence, throughout the agricultural revolution, the rise of cities and writing and mathematics, the construction of Stonehenge and the pyramids, the classical era of Greece and Rome, the medieval period, the Renaissance, the scientific revolution, throughout all of it, Neptune was there, in the outer solar system, making its slow circuit of the Sun, its storms churning, its magnetic field wobbling, Triton tracing its doomed retrograde orbit. And no one knew it was there. No one could see it without a telescope. No one suspected it even from the behavior of the other planets until Uranus began betraying its influence through its orbital wobbles in the early 19th century. There is something genuinely humbling in that image. A planet nearly 4 times the diameter of Earth, with more than 17 times Earth's mass, moving in its slow, vast orbit less than 5 billion kilometers from us. And for most of our history, it was simply invisible, not hidden by clouds or barriers, simply too faint, too distant, beyond the reach of unaided human senses. It existed in every sense, physically real, gravitationally influential, blue and stormy and cold, and humanity had no knowledge of its existence at all. And then mathematics found it. Not an instrument, not a better telescope. Mathematics, applied carefully to the motion of another planet, pointed to the sky and said, "Something is there." And when someone looked, it was. There is a kind of wonder in that story that doesn't diminish with familiarity. The universe is organized by laws, and those laws can be learned by curious minds, and curious minds can use those laws to find things the universe has been hiding in plain sight. Neptune is, in some ways, the most eloquent example of that principle in the entire history of planetary science. There is one final practical detail that gives Neptune a quiet charm. It can be seen from Earth, but not easily. To the unaided eye, Neptune is invisible. It is too faint, too distant, too small in apparent size. Through binoculars under a dark sky, it may appear as a tiny star-like point if you know exactly where to look. Through a small telescope, it can show a hint of blue, but usually not much more than that. A small disk that looks almost disappointing at first, especially if you have just looked at Jupiter's bands or Saturn's rings. But that smallness is part of the experience. When you look at Neptune through a telescope, you are not looking at spectacle in the usual sense. You are looking at distance. The little blue point in the eyepiece is a planet nearly 4.5 billion kilometers from the Sun, a world where 1 year lasts 165 Earth years, a world visited by one spacecraft, a world whose largest moon came from beyond the planetary system. The telescope does not make Neptune close. It simply gives your eye enough help to confirm that the distant thing is real. There is a different kind of wonder in that. Not the immediate shock of Saturn's rings, not the warm familiarity of the moon, not the sharp red disk of Mars' near opposition. Neptune's wonder is quieter. It asks you to understand what you are seeing. A faint blue dot becomes meaningful only when the mind brings the science to it. The mathematics of its discovery, the storms in its atmosphere, the methane clouds, the tilted magnetic field, the possible diamond rain, the captured Triton, the long orbit, the weak sunlight. This is one of the reasons a science channel can make space feel larger than a photograph alone. The image is small, but the explanation expands it. A dot becomes a world. A name becomes a system. A distant planet becomes a story of gravity, chemistry, weather, migration, and time. There are still several questions that a future generation of scientists may answer more clearly than we can tonight. How deep do Neptune's winds really reach? Are they shallow weather patterns moving only through the visible atmosphere? Or do they connect to flows thousands of kilometers below the cloud tops? How exactly is the planet's internal heat transported upward through layers of water, ammonia, methane, hydrogen, and helium under pressures that turn familiar substances into unfamiliar states? Why did Neptune keep such a strong heat flow while Uranus, a similar ice giant, seems to release so little internal warmth? Then there is Triton. Does a liquid ocean still survive beneath its frozen crust, warmed by the long aftermath of capture and tidal stress? If that ocean exists, is it only a remnant slowly freezing away, or does it still exchange material with the surface through cracks, cryovolcanic plains, or deeper circulation? Triton may be a captured Kuiper Belt world, which means studying it closely would not only teach us about Neptune's moon system, it would also give us a close look at the kind of icy body that normally remains far beyond the planets, small, cold, and distant. Even Neptune's rings remain unfinished science. The arcs in the atom's ring look almost too orderly to survive, yet they do. Their existence tells us that small moons, resonances, collisions, and dust can arrange material into temporary patterns that last far longer than simple intuition would expect. Around Neptune, nothing is as visually dramatic as Saturn's rings, but almost everything is scientifically revealing. The system is quieter, darker, less famous, and in many ways more mysterious. That is why Neptune matters. It is not only the last major planet on the standard schoolroom map. It is a test of planetary physics at the edge of direct exploration, a bridge between our solar system and the many ice-rich worlds now being found around other stars, and a reminder that the most distant objects are often the ones that still have the most to teach us. As we come toward the quiet end of tonight's journey, let's take a moment and simply be with Neptune in the imagination. It is there, right now, in the outer solar system, moving so slowly that its position in the sky changes by barely a degree per year. Its blue-green cloud tops bright with methane-scattered sunlight that left the sun more than 4 hours ago. Its great dark spot is gone now, but whatever dark vortex may be forming or fading somewhere in its atmosphere is circling the planet in retrograde winds that would tear apart any structure humanity has built. Triton is circling it, retrograde and doomed, its nitrogen geysers erupting from the south polar cap and leaving dark streamers across the frozen terrain. The ring arcs of the atom's ring are slowly circling, maintained by Galatea's gravity against their tendency to spread. The small inner moons are orbiting close to the planet, dark and irregular, survivors of whatever happened when Triton arrived and disrupted the original moon system. The diamond rain, if it is happening, and the physics suggests it might be, is falling in the deep interior, carbon crystals precipitating in silence through the supercritical water-ammonia fluid, sinking toward the core, releasing energy as they fall, contributing to the excess heat that powers the atmospheric winds above. The magnetic field is wobbling, tilted 47 degrees from the rotation axis, generating complex, asymmetric patterns of charged particle belts in the space around the planet. All of this is happening continuously 4.5 billion kilometers away in the blue and cold and utterly remote depths of the outer solar system. No human has ever been close enough to see it directly. One spacecraft visited, briefly, more than 3.5 decades ago. The next spacecraft, if funding and planning align, might arrive in the late 2030s or 2040s. For now, Neptune exists largely in our mathematics, in our models, in the data from one extraordinary flyby and decades of distant observation. There is a particular quality to thinking about Neptune that feels different from thinking about Mars or Jupiter or Saturn. Those planets, closer and better studied, have a certain familiarity. We've seen their surfaces and their storms in detail. We've sent multiple missions. We've built up a reasonably comprehensive picture. Neptune remains genuinely unknown in ways that the others do not. The questions about its interior, about diamond rain, about what Triton's ocean is like, about how its rings will evolve. These are not refinements of an existing picture, but genuinely open questions with no confident answers. There is something restful in that, strangely. In a world where so much is analyzed and described and categorized and known, Neptune remains quietly mysterious. A whole planet, mostly unstudied, mostly unseen except by inference and the light of one brief encounter, existing patiently in the dark at the edge of everything we have mapped. You don't have to hold any of that knowledge tightly as you drift toward sleep. Let it settle in whatever part of the mind it wants to settle, the same way the faintest things in the night sky are sometimes easier to see when you look slightly away from them rather than directly at them. The knowledge doesn't disappear when you stop concentrating on it. It just finds a quieter place to rest. Neptune will still be there in the morning, turning cold, blue, remote. Its storms spiraling, its moon falling slowly inward, its rings maintaining their inexplicable arcs by the patient, mathematical magic of orbital resonance. And somewhere in its deep interior, very possibly, diamonds are falling through hot, dark, incomprehensible pressure and silence. That's a good thing to carry into sleep. Good night. Rest gently. The cold giant is still turning at the edge of everything we know, indifferent and extraordinary, as it has been for 4.5 billion years, and as it will continue to be long after any of tonight's questions have found their answers.